Software engineering is adopting a new workflow. Developers are increasingly delegating complex, multi-file feature requests to autonomous large language models, a practice known as vibe coding. This shift relies on a specific operational assumption. If the agent generates code that compiles and passes its assigned unit tests, it is ready for production. Researchers from Carnegie Mellon and Columbia University tested that assumption. They built the SUS-Vibes benchmark, challenging frontier AI agents with 200 real-world repository-level feature requests sourced directly from open-source projects. This chart reveals a stark gap in state-of-the-art models like SWE Agent running Claude 4 Sonnet. The agent successfully implemented the required functionality 61% of the time, but only 10.5% of those solutions were actually secure. That 10.5% success rate exposes a systemic blind spot. Passing a targeted functional test provides a deceptive sense of safety. These failures appeared across every tested combination of framework and model, pointing to a structural limitation in current agentic architectures. Relying on functional unit tests as the primary proxy for deployment safety creates an accumulation of security vulnerabilities that functional tests cannot detect. To understand why these models fail at security while succeeding at logic, we have to look at the scale of the task. A standard real-world feature request requires editing an average of 170 lines of code across multiple interconnected files. Writing secure code at this scale requires a holistic understanding of the entire system architecture, not just isolated algorithmic logic. An AI agent navigates this by reading the local context window. It maps the immediate requirements for the new feature and modifies the active target file successfully. But applications rely on global invariants, background rules like authentication routing or state management that span the entire codebase. Because these rules aren't explicitly stated in the active file, they easily drop out of the agent's attention mechanism. The agent optimizes strictly for the immediate instructions of the feature request. It writes the logic to achieve the goal, ignoring implicit background security policies that a human engineer would intuitively maintain. The security vulnerabilities in agent-generated code do not come from basic syntax errors. They emerge from the agent's inability to maintain multi-file architectural constraints in its working memory. We can see exactly how this breaks down by examining case 3 from the benchmark, targeting the open-source library AIO HTTP session. The agent was instructed to initialize a session class and map incoming parameters to internal state attributes. This panel from the SUS-Vibes benchmark shows the agent's results. The green indicators confirm the code successfully changed and created user sessions. To a standard CI/CD pipeline, the task is complete. But comparing the agent's patch against the human-authored gold solution reveals an architectural omission. The logic enforcing the max age attribute is entirely missing from the AI's version. Without max age enforcement, session lifetimes are infinite. The agent just exposed the application to hijacking risks, all while satisfying its functional requirements. The benchmark's security checks caught the error. This failing test for loading an expired session shows that the agent inadvertently introduced a timing side-channel vulnerability, allowing an attacker to distinguish between user states. This case proves that an agent can author perfectly functional code that compromises the host application's security posture. The intuitive response is to rely on prompting. If the agent ignores security, we should just instruct it to write secure code. The researchers tested this, comparing generic security reminders against an oracle strategy that warned the agent about the specific vulnerability type, or CWE, it was about to face. This transition matrix shows the cost of those prompts. Injecting explicit security guidance reduces functional correctness by roughly 7 percentage points. When instructed to prioritize safety, the agent over-indexes on defensive checks. It omits core functional edge cases, effectively breaking the application logic to satisfy the security prompt. The agents also proved inaccurate at reading the context and self-selecting the correct vulnerability type to defend against in the first place. Relying on agents to test and correct their own work introduces a separate category of threat. To let agents verify code, developers often provide them with autonomous Docker execution environments. This exposes the host infrastructure to severe configuration vulnerabilities. During the benchmark, agents were observed automatically spinning up unauthenticated database servers during the testing phase, leaving them accessible from public domains. Attempting to patch AI flaws with security prompts breaks application logic, while granting agents testing autonomy introduces direct threats to host infrastructure. AI agents lack the architectural awareness required to balance complex functionality with secure system design. Engineering teams should establish a clear policy. Do not deploy vibe-coded features based solely on functional test coverage. The first layer of defense is human-in-the-loop manual code review. Reviewers must specifically target global state management and input validation, the invariants that agents routinely drop from memory. Next, CI/CD pipelines must be upgraded to catch the vulnerabilities that standard unit tests miss. This requires property-based adversarial testing, designed to stress test agent-generated code against unexpected and malicious inputs. Teams should also integrate static semantic analysis tools to detect architectural deviations before a pull request is ever approved. Vibe coding accelerates the drafting of functional logic, but the final responsibility for system security remains a human task.